I am going to be utilizing a teeter-totter or seesaw example in order to describe the Le Chatelier principle. So what does this principle say? Say you have reactant A and reactant B, and that forms into C and D. Mnxy refers to the coefficient of this balance equation. Well, it also has the ability to go in a reverse direction where the C and D forms into A and B. And this point in time where the teeter-totter is evened out or balanced, not necessarily in concentration, but it is at equilibrium. So this balance point is at equilibrium. All right? At equilibrium. But there is a point in time in which there is an imbalance. Say some stuff has been added or like reactant, like this left side of the equation, there's some kind of stress on it, okay? Meaning more has been added, more has been put on, or less, this C and D has been removed, okay? Or this portion, there is a less weight that has been taken out. Well, the teeter-totter will move such that this left-hand side will be it will fall forward. So, or fall down. So it's going to do whatever it takes to re-establish the equilibrium. So it's going to want to favor the forward direction. So in this scenario, it's going to want to go in the forward direction. So favors forward direction to reestablish the equilibrium. What about in a case where more of the C and D, the product has been added? Some kind of stress has been done on the right side so that more stuff has been added there, or perhaps less of this has been removed, or some of the A and B has been removed, I should say. Then what's going to happen is going to want to go in a reverse direction, so it really re-established the equilibrium back to this point. So this favors the reverse direction. So in a case, all of these, they're doing whatever it can to reestablish the equilibrium. So if something causes for the reaction to go out of the equilibrium, the reaction will try to reestablish that, either going into the forward direction or to the reverse direction. And this is what the principle says, is that if an equilibrium system is stressed, meaning it was at equilibrium, but something happened to it, it's going to experience a shift in response to the stress, so that reestablishes the equilibrium. Now, there are several ways in which these equilibrium factors will be stressed, and we're going to be discussing the ways that reaction can go out of the equilibrium. And the very first one is the change in the concentration. So say if you have hydrogen and iodine forming into hydrogen iodide, and then this also has the ability to go into the reverse direction. And right now it's at equilibrium. The Kc is value of 50 at 400 degrees Celsius. Now, what will happen if I change the concentration of the reactant? Say I add in more of the reactant. If I add in more of the reactant, what's going to happen? It's going to go into the reverse. Oh, I'm sorry. It's going to want to go in the forward direction. Well, I was just testing you. Okay, it's going to want to go in a forward direction. So this point is when the reactant is added, right? So this is time when reactant is added. That's why it went into teeter-totter mode. Or maybe perhaps you have removed the product. That's why it went in teeter-totter mode. This is a point in which the QC, okay, the reaction quotient, is less than the Kc. When the reaction quotient is less than the Kc, the reaction will go into the forward direction. In another scenario, when the teeter-totter is on the other end of the spectrum, where in which the product side seems like there's a lot of weight has been put on that side of the teeter-totter, meaning more of the product has been added or some of the reactant has been removed. So this is concentration differences happening here. And so if the product has been added or the reactant has been removed, then we have established where the QC, or the reaction quotient, is greater than the Kc. So this point is when now it's going to want to favor the reverse direction in order to re-establish the equilibrium. So all of these guys are based off of the change in the concentration, and to re-establish the equilibrium, they're going to either go in a forward or reverse direction. So second way, in order for a reaction to go out of equilibrium, would be a change in temperature. So I have here N2O4 forming into 2 nitrogen dioxide. The delta H value here says 57.20 kilojoules. This just means that there has been heat added, or 57.20 kilojoules been added, in order for the reactions to go. But note, it's a positive value, and what this positive value means that the heat has been added on the reactant side. If it's a negative value, it will be added on the right side of the equation, the heat in itself. Now, think of heat as almost like the same as concentration. If I were to add the heat on this side, and this is a endothermic reaction, this is endothermic, since it's a positive delta H value, that's going to cause a lot of stress on this side. So the teeter-totter is only very heavy on this side. Then what's going to happen is going to want to go towards the right side of the equation to reestablish the equilibrium. So it will go into forward direction. Now, let's say if we were to decrease the temperature, so I'm going to remove that heat, then the teeter-totter will go in such way that this side is heavier. And so then that's going to do is it's going to reverse its direction and go to equilibrium will shift to the left. So it will favor the reverse direction. And this works opposite way for an exothermic reaction, where the heat is now on the right side of the equation. It's on the product side. So if I raise the temperature over here, the heat is going to, the reaction will want to go into the reverse direction. And if I remove the heat, then it's going to go to the forward direction. So let's do a learning check based on what we have learned so far. So just 4 ways in which the concentration of hydrazine could be increased. Okay, so meaning the concentration, this could be increased in an equilibrium described by the following equation. I'll do one and you could come up with the other 3. So this shows that if I were to increase this, right? If I want to increase this, I will have to probably, if I were to add more of the nitrogen, it's going to push the reaction forward. So adding N2 concentration or increasing N2 will produce more N2H4. So that's my 1. Can you come up with the 2, 3, and 4? Come back. So here are some additional ways: adding H2, removing the N2H4, and also reducing heat will help in order for more hydrogen to be formed. I like to bring in the topic of catalyst here. Now, catalyst is not going to change the equilibrium constant, okay? It's not going to cause any of the reaction to go out of equilibrium, but I do want to put it in here. Addition of the catalyst means that it's going to lower the activation of energy, which means that if I were to have something like a reaction, carbon and oxygen, oxygen forming into carbon dioxide, something like this. If I were to add a catalyst in here, some kind of system where in which it's going to grab the carbon and oxygen and put it together and then spit it out. It has the ability to do reverse. It's going to grab onto the carbon dioxide and split it open and then spit it back out this way. The thing is, a catalyst isn't really dependent on whether like I need to shift to the left or right. It's just going to happen with whatever it grabs. So the catalyst, what it does is it's going to just make the reaction go faster, whether reverse go faster or forward faster, but it's not going to affect the equilibrium constant. So it's not going to shift the equilibrium. So this has no change on the equilibrium in itself. Just makes the reaction go faster. That's all it is. Okay, let's do a learning check now. Methanol can be prepared from carbon monoxide and hydrogen at high temperature and pressure in the presence of a suitable catalyst. So you're going to take a close look at this equation and also the enthalpy. It's a negative value, by the way, and answer these series of questions and come back and check the key. And here is the key.